Thank you. It's recording now. Okay. Dimethyl sulfoxide is one of the polar aprotic solvents. And then we have the DMF. We had one example the other day for acetone, and that was also aprotic solvent. So N-dimethyl formamide. So you learn about this functional group. You already learned about the functional group of the amide. Is coming from formic acid, one carbon amide, so it's formamide. You have two methyl groups attached to it, so it's a dimethyl formamide. But at this point, the concern is not the naming of the compound. The concern is that to recognize these compounds, they are polar and there is no ionizable hydrogen. That means there is no hydrogen attached to the oxygen. So if we have a weak base, for weaker base, they are good solvent, good nucleophile in polar solvent. But if you have a strong base, they are better nucleophile in the non-polar solvent. So what about these aprotic solvents? Aprotic solvents, they can solvate the positive charge, but they are not solvating the negative charge. So let's say if you have a KF, where we looked at fluorine already being very weak nucleophile. So fluorine is not good nucleophile, but when you bring it as a KF and you bring one of the solvating proper solvent that takes the potassium with the positive charge away from fluoride, then fluoride basically doesn't have a choice. It can go and attack a nucleophile as a nucleophile. So it can work as a nucleophile when it's not engaged with the potassium anymore. What is a nucleophile agent? Any of these groups, they can be acting as a nucleophile. Anything with a negative charge or pair of unshared electron is acting as a nucleophile, meaning that it looks for nucleus. So if you have a carbon with the partially positive charge, when you have halide with partially negative charge, this carbon, it's like it counts as a nucleus, and then any of these nucleophiles, they can attack the carbon with the positive charge from alkyl halides. Remember, we are working with the reactions of alkyl halides, and we are studying the mechanism of reaction. We're trying to find out what type of condition is going to promote or enhance the reaction to go through Sn2 reactions, and what conditions does not help Sn2 mechanism, because there is a difference in the product of the Sn2 versus Sn1 reactions. So if we are going to soon talk about the Sn1 reaction. So let's say if your reaction goes through Sn1 reaction, so you have X and then you have R prime and you have R and you have a hydrogen here. For Sn2 reactions is going to give only one product. And let's say if you want to get the hydrolysis, Sulwalysis of this, you get the OH on the opposite side, and then you have your R and the hydrogen. So for Sn2, configuration is going to change. If you start with S, it can give you R. If it starts with R, it can give you S. But for Sn1 mechanism, you are going to get a mixture of two products. So it's better if I put this as a nucleophile, and then I have the three other groups attached to it, plus the nucleophile could be on the right side, and you have your other groups attached. So for Sn1, you're going to get 2 products. For Sn2, you're getting only 1 product. So that's the difference. So we want to find out about conditions that is going to give us Sn2 product, or coming from Sn2 mechanism, or the conditions that is coming from the Sn1 mechanism. So we are going to compare these two. The factors that we have compared so far is the nature of the alkyl halides, how bulky it is, and for the Sn2, methyl was better than primary, and better than secondary, better than tertiary. And in terms of the nucleophile, the better nucleophile, a stronger nucleophile is going to promote the reaction via Sn2. And what was the strong nucleophile? We talked about the strong nucleophile, a weak base as a strong nucleophile. So Hi is a strong acid, and I minus as a result is a weak base and is a very good nucleophile. At the same time, is polarizable, so it's going to act as a better nucleophile. So the stronger the nucleophile, the better condition for the reaction to go through mechanism, the Sn2 mechanisms. So we also learn about some of the different type of the solvents, if it is aprotic, polar aprotic, or if it's a non-polar, or if it's a polar protic solvent. The effect of the steric effect for the nucleophile. For Sn2, if you have less bulky group is better. Why less bulky group is better? Because for Sn2, remember the backside attack. The bulkier the group is, the harder for it to get into the carbon with the positive charge. So if you have 3 groups already here and you bring this bulky group, it's going to be hard for it to go in and form bond with the carbon. But if you have a smaller, so less bulky base or less bulky nucleophile, is going to be better for the Sn2. For Sn2 mechanism, less bulky, it's going to be better than bulky group because of the steric hindrance. So the same way that tertiary alkyl halide is going to be slower via Sn2 mechanism, bulky nucleophile also is going to slow down the reaction. So T-butoxide ion as a strong base is not a good nucleophile, but etoxide here is coming from two carbon alcohol, like ethane, ethanol, and then etoxide, ethanol losing hydrogen. So with the etoxide ion, it's going to be better nucleophile for Sn2 mechanisms. Okay. So we said that tertiary compounds, tertiary alkyl halides, they don't go through substitution reaction. This is a tertiary alkyl halide, but by the experimental observation, it shows that this reaction actually goes fast. And because it goes fast, it kind of contradicts with everything we learned about the substitution reaction before knowing anything about Sn1 reaction, actually. So when we see this observation in experimental, based on our experiments, that this reaction actually goes fast, then the idea of this must follow a different mechanism. Is being entertained and proven that this reaction actually takes place, but it's placed with the different mechanism. Why not Sn2? Because this group is very bulky, so it's not good for Sn2. The nucleophile is a weak nucleophile, and weak nucleophile is not good for Sn2 reaction. For Sn2 reaction, we want a strong nucleophile, we want a primary or methyl alkyl halide, and none of them exist here. So you have a very weak nucleophile and you also have a very bulky alkyl halide. but yet this reaction happens and you get very fast reaction. So you get a lot of product, high % yield of this product. The explanation is that this is going through a different type of reaction, then the different type of mechanism. So then they had to find out what is the mechanism of this reaction. So they found that the reaction actually goes through 2 steps. So a different reaction mechanism. And that reaction was a Sn1 reaction, which S stands for the substitution, and N for nucleophilic, and 1 stands for unimolecular. So this is a unimolecular nucleophilic substitution reaction. So in unimolecular substitution reactions, what does it mean? It means unimolecular means that only one compound is engaged or involved in the rate determining step, and that is the concentration of alkyl halide only. And the concentration of nucleophile, if you increase the concentration of nucleophile, it doesn't change the rate of the reaction. That's for Sn1. For Sn2, if you remember, we have the rate of the reaction, that is K, concentration of the alkyl halide, and concentration of the nucleophile. But for Sn1 reaction, or where you have a tertiary, if they change the concentration of nucleophile, the rate does not change. That means this reaction does not, the rate of the reaction is not affected by concentration of the nucleophile. R is the alkyl group. So R is the representative group. So any alkyl group or aryl group, so it can be represented by R. And X is coming from group 7A periodic table, and that is halide. So it could be chlorine, bromine, iodide, or fluoride. So the rate of the reaction for Sn1 depends on only concentration of the nucleophile and not the concentration of the alkyl halide, not the nucleophile. The other observation that they had, if you have a tertiary alkyl halide, the reaction is much faster than if you have secondary, then you have a primary or methyl. Basically, primary and methyl are not good candidates for Sn1 mechanism. But if you have secondary, it's faster than primary and methyl. If you have tertiary, that would be the fastest. And that goes to that was another proof that it's this reaction has an intermediate, and the intermediate that was forming was a carbocation. And the carbocation, since tertiary carbocation is much more stable than secondary, than the primary, than the methyl, as a result, the more stable intermediate is going to yield major product. More stable intermediate, that means lower activation energy. More stable intermediate means faster reaction. And numerical values here proves that we do have much faster reaction for tertiary compared to secondary. Primary and methyl are not good candidates for Sn1 type reaction. So the rate of the reaction, so these are the experimental findings. Experimental findings, rate of the reaction depends only on concentration of the alkyl halide. So only alkyl halide must be involved in the rate determining step or transition state of the rate determining step. Replacement of the hydrogen atom with methyl group is not going to be easy, and then when you have the alkyl substitutions, is going to be faster. So for Sn1 reaction, methyl group and the primary are not good, but secondary and tertiary are. The reaction of alkyl halides, when you have asymmetric carbon, is going to yield to 2 different products. So basically they are racemized, or you get the racemic mixture or racemic mixture. That means if you start with S reactant, you will end up with mixture of R and S product. For Sn2, you would get the inversion in configuration. So if you start with S, you end up with R, and vice versa. But for Sn1 reaction, if you start with S, you get mixture of R and S. If you start with R, you get mixture of R and S. So for the Sn1 reaction, the leaving group is going to leave first before nucleophile comes in. So we do have a two-step reaction. So step 1, nucleophile leaves. Step 2, step 1, leaving group is going to leave. Step 2, nucleophilic attack would take place. So you have two-step reaction. And anytime you have two-step reaction or more than one-step reaction, you have to look at your energy diagram to find out what is the rate determining step. The rate determining step is the step that is the slowest step. We learned that in chapter 4. And the slowest step of this reaction is going to be step with the highest activation energy. So the first step of this reaction, which is formation of carbocation, has highest activation energy, or is the slowest step of this reaction. And that makes formation of carbocation to be rate determining step. So tertiary carbocation is going to form faster than secondary than primary. And now it explains why substitution around the carbon of the nucleus, or the carbon with the positive charge, carbon with carrying the alkyl halide functional group, is going to increase the rate of the reaction for Sn1 type, or with the Sn1 mechanism. So formation of the carbocation is the rate determining step. So in the slow step, the leaving group leaves. In the fast step, because you have like very reactive intermediate, carbocation is not stable, so it's very reactive, and that reactivity of carbocation is going to make the next step much faster. So you have a fast step of the reaction, that the nucleophile comes in and forms bond with the carbocation. Hydrogen here, there's when the water is acting as a nucleophile. When water acts as a nucleophile, when it forms with the bond with the carbocation, water is neutral, doesn't have any charge. You don't have a negative charge on water molecule. Carbocation has a positive charge. So that positive charge is going to be shared between the carbon and oxygen, because this nucleophile is coming to help the nucleophile to be more stable. So it's going to take over that plus charge. And when it takes over that plus charge, it's going to make the oxygen very uncomfortable, because oxygen has very high electronegativity and does not like the plus charge. So since it doesn't like the plus charge, it's going to make the whole molecule unstable. Because it's very unstable. And why is unstable? Because of the plus charge on the oxygen. Why didn't we put the plus charge in other places? Because that was the role for our nucleophile to come in and help the carbocation to be stable. So it's going to say, okay, give me your plus charge, I'm going to help you. So it takes the plus charge in, and that makes it very uncomfortable intermediate again. So we don't have product yet. This is a second intermediate, but it's forming very fast and is acting very fast. Why is acting very fast? Because it's very unstable, and by losing hydrogen, it's going to become a final product. Now, how do we take this hydrogen? You can abstract the hydrogen by water molecule. The solvent in Sn1 reaction often acts as a base that is going to remove the hydrogen. Whenever you have O plus attached to two hydrogen, and this could attach to another carbon, or it could be attached to to a cyclic system. So when you have this situation, you have two choices, and please remember, all from now, for organic 1, organic 2, anytime you have a plus charge on carbon, this is going to that sharing bond between the oxygen, then the plus charge on oxygen is very unstable. And because it's unstable, you have two solutions, two options. One, remove water. If you remove water, what's going to happen? Is going to go back to what we had before, basically goes back to this step. And there is no benefit to that. We don't have product. You remove water, you end up with carbocation that is very unstable. So you go from one unstable to second more unstable. So there is no benefit. What is the other choice? The other choice is remove the H plus. So you remove hydrogen with the plus charge. And how can you remove H plus? H plus traditionally, or from 1045, 1046, from general chemistry, you have learned that H plus, it represents acid, right? So if you want to remove H plus, you have to bring in base. That's why I said earlier, the molecule of the solvent, it can act as a base, and I had to explain why you need a base. So the molecule of the solvent can act as a base and is going to remove H plus. Why do we have to remove H plus? Because oxygen cannot carry positive charge. And in order to stabilize this, you have to remove the plus sign from the oxygen. There are two choices. And if you write down in your own word, it's going to make it easier for you to understand later, because we are, for every time you are doing this type of reactions, and it's a lot of cases, chapter 7, 8, 9, and then 10, you get to this situation that you have oxygen carrying the plus charge, and you want to make sure that is going to remove the plus charge. Use one of the two options: remove water or remove H plus, whichever yields to better product or desired product. What you want to do today, like for this reaction, you want to replace the Br with OH, and the only way that to remove that is going to be removing hydrogen with the plus charge, and then you end up with one hydrogen left. That's your OH attached to the T-butyl group. So only alkyl halide must be involved in this transition state of the rate determining, which is the first step. And using more substituted alkyl halide, that means tertiary goes faster than secondary, goes faster than primary. What makes the tertiary alkyl halide to go faster? Because a tertiary carbocation is more stable than secondary, and more stable than primary, more stable than methyl, because your intermediate is going to be more stable. So primary and methyl carbocation are very unstable alkyl halide for this type of reaction, so they don't go through Sn1 reaction. But we already know another mechanism that is going to be preferred for this type of alkyl halides, either methyl or primary, and that was the Sn2, when we want less bulky groups. I also said that you get two types of product. You get two mixture of two products for Sn1 mechanism, and the reason for that, when you get the carbocation is going to be sp2 hybrid carbon, because you only have 3 domain or electron domain or 3 groups attached to carbocation. When you have sp2, then you also have a p orbital that is unhybrid with any sp2 hybrid orbitals, if you remember from the chapter 1 or 2. So you have your sp2 hybrid orbitals, and then you have a p orbital that is perpendicular to the sp2. So if you have sp2, 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 this is going to be the p orbital. That is just the 2 loop of 1 p orbital that you have there. Now, your nucleophile, it can attack from this side or this side, from the top loop or the bottom loop of the p orbital. And as a result, the heavy group, it can be on the right side, or the heavy group can be on the left side. If the starting material that you start with your alkyl halide is asymmetrical or is a chiral compound, your product is going to be chiral. If the starting compound is not chiral, you get only one product because it's not going to matter. So if it's achiral, there is no R and S, and there is going to be no R or S question for the product. But if your reactant is R, for example, because we don't know these groups, so we can't say R or S, but if it is R, then you end up with a R product and S product. One product with retention of stereochemistry, one product with inversion of the stereochemistry. So you get two mixture of two products. You get pair of enantiomers. So you get a complete, you get a racemic mixture. Is it going to be 50-50? If the H2O is coming from the same side that the Br is leaving, okay? If it's coming from the same side, H2O has pairs of unshared electron and oxygen. Br minus or bromide is going to be rich in electrons, so you have too many electrons in the around Br and H2O. So if H2O is coming from the same side that bromine is leaving, is going to be shy, is going to be hindered, or is going to be repelled by the Br. But if it's coming from the opposite side, it's going to be more free. It's much easier because the Br is already detached, but is in the neighboring, is in the neighbor still right here. So still coming from H2O from the same side is going to be repelled by the electrons that you have from the Br. But going from the other side is going to be, from the back side attack, is going to be easier for H2O. So you might get more of the product that is coming from backside attack, less of the coming from, less with the retention, more of the inversion. So you could get more percentage of the inverted product. And if it says 50-70, that really depends on how fast the Br is leaving, or how easy, how bulky is the leaving group, and what's the electron density. But the inverted product is going to be more. So it depends on where the halide is located. Yes, let's go like one explanation right here with this molecule down here. So if the halide leaves, then the nucleophile is coming. Now, if the nucleophile is coming from the side that halide is leaving, that's one choice, and the opposite side is the second choice. So you have two choices. One, coming from the same side that the leaving group is leaving. The other one is going from the opposite side. If it goes from opposite side, you get inverted product. If it comes from the same side, you get the retained product. So the configuration is going to be the same. So because of the electron density or the electron repulsion, negative charge, repulsion between the leaving group and the nucleophile, this is going to yield smaller percentage of the product compared to the backside attack. Yes, so it depends on where is the halide or the leaving group attached to the original molecule. So going from the backside attack is going to be easier because the BR has left but has not diffused away. So that's why I said that it's still in the neighborhood. So because it's still in the neighborhood, coming for the nucleophile from the same site is going to be not as convenient, or is not going to be as easy as coming from the backside. Let me read the comment you had. What is the difference between the retained product and inverse product? Okay, inverted product meaning that if you have R, it changes to S. If you have S, it changes to R configuration. Retained meaning if you start with R, you end up with R product. If you start with S, you end up with S product. That means configuration has retained, it stayed the same, or configuration has been inverted, means that configuration has changed from one to the other. If it's R, it has changed to S. Leaving group, better leaving group is best for both of the Sn1, Sn2 in general, but for Sn2 is a lot more, the effect of the leaving group is more significant for Sn2. And then nucleophile for Sn1, the strength of the nucleophile is not significant for Sn1 because nucleophile is not involved in the rate determining step. If you had a very strong nucleophile, most likely it would have attacked the carbon alkyl halide before the leaving group leaves, and that translates to Sn2 type reaction. So in Sn2, nucleophile comes in before the leaving group has left already, but in Sn1, the nucleophile is going to stay until the leaving group leaves, and when the leaving group is gone, and then it's going to come in. So nucleophile comes in after the leaving group has left in Sn1 reaction. The Sn1 reaction, so since the strength is not a concern, a strength of the nucleophile, often the solvent is used as the nucleophile, and since when the solvent is used as a nucleophile, like water or alcohol, the type of reaction is also called Sulwalysis. Sulwalysis, like if you have water as the solvent, and water is acting as the nucleophile, which it can act as a nucleophile in Sn1 type reaction, then the reaction is called Sulwalysis, or the general reaction is called Sulwalysis. Okay. Benzylic and allelic, they will go through Sn2 type reaction. So benzylic and allelic. If they're tertiary, it would always be Sn1. But if it's a primary, or for primary, it's going to go to Sn2. So primaries, Sn2. If it's tertiary, it's going to be Sn1. Now, I guess the question is what's going to happen if you have a secondary. If you have a secondary, it's going to be a different situation. So if you have allelic carbocation, what is allelic carbocation or allelic alkyl halide? Allelic means that whatever you have, that you're going to make it followed by allelic. So allelic carbocation or allelic alkyl halide, meaning that is adjacent to carbon that carries carbon-carbon double bond. So this carbon is adjacent to this carbon with the double bond. So for Sn1 reaction, your allelic alkyl halide is going to yield allelic carbocation. So when you have allelic carbocation, it can form resonances. So you get formation of resonance for allelic carbocation. How does resonance form? Resonance, as you practiced in chapter 1, is delocalization, or just changing the arrangement of the electrons. The backbone of the molecule stays the same. Plus or minus charges can be moved around. Pi bond can be moved around when possible. And when you get resonances, it's going to make it even more stable. Your intermediate is going to be more stable. So when you have the plus charge in this allelic position, the pi bond can move. The plus charge is going to jump by, so pi bond moves by one bond. So if it was between carbon 1 and 2, now it goes between carbon number 2 and 3. And the plus charge jumps by 2 carbon. Basically, for this carbon, it doesn't matter if the pi bond is on the left side or on the right side. It still is sharing electrons, or number of electrons does not change for the carbon in the center. But if the pi bond moves from the left side to the right side of the carbon in the center, the carbon, the most left carbon, is going to be left with the electron deficient, and that's why it's going to be positively charged. And when the pi bond moves between carbon 2 and 3, or to the right side of the carbon in the center, is going to satisfy the carbon that we had the plus charge on, because it's now gaining electrons. So the plus charge, it doesn't make sense here anymore. That plus charge is going to be assigned to the carbon that has lost the pi bond. So when the pi bond is moving, let me just put it this way. When the pi bond is moving from left side to the right side, this carbon here is gaining a pi bond from here to here. This carbon here is gaining a pi bond. This carbon here is losing a pi bond. The carbon losing the pi bond is going to gain the positive charge. The carbon that is gaining the pi bond is going to lose the positive charge. So it's either pi bond or the positive charge. And we already know pi bond means pair of electrons. So if the carbon on the right side is gaining the pi bond, that means it's gaining electrons. So there's really no positive charge there anymore. The positive charge is going to be assigned to carbon that is losing the pi bond. So as a result, what you are going to have as a result is that you get mixture of two intermediates. See that these two are separated by double arrow, and those are the intermediates. So you get mixture of two intermediates. If you get mixture of two intermediates, as a result, you are going to have two products. When you get two products, in this case, the name of the product is not going to change. So you are going to get, let's see, you are going to get the OH attached to the first carbon from the right, or you get the OH attached to the second carbon. So in this case, it's not going to make a difference, because is either way, OH would be on the carbon 1, and then the pi bond is going to be on carbon number 2. It's not going to make a difference. So if the OH attaches to this carbon OH or this carbon OH, if it attaches, it gives you only one product. This is a different example. With a different example you have down here, when you have 4 carbon. Now we get two intermediates. You get allelic carbocation that is going to give you resonance, and when you have the resonances, you get two intermediates. In this case, when you go back with the 3 carbon, the first example A, your allelic carbocation here is a primary allelic. in this case is also primary allelic. So it's not just primary, it's just primary allelic. And this is a primary allelic. When you come to the second, to example B, you get a primary allelic, and here you get a secondary allelic. Which one is going to be major product? Which one is more stable? Primary allelic or secondary allelic? Which one would be more stable? Okay, let's put it this way. Which carbocation is more stable, primary or secondary? Which carbocation is more stable? Tertiary, secondary, primary, and the methyl, right? So always the higher order carbocation is going to be more stable. So secondary is more stable than primary. And since secondary is more stable than primary and both of them are allelic, secondary allelic is going to be more stable than primary allelic. Allelic adds a stability, but in this case, comparison is apple to apple. Both of them are allelic. So secondary allelic versus primary allelic, for secondary allelic is going to form faster. So when we look at the intermediates, we get more stable intermediate for secondary allelic, less stable intermediate for the primary allelic, and then it's going to form product. Okay? It's going to form the product. When you get the product, your secondary allelic is going to give you carbon-carbon double bond on the first carbon, and your primary allelic is going to give you carbon-carbon double bond between carbon number 2 and 3. So you get the 2, 3 between carbon number 2 and 3. Here you get between carbon 1 and 2. This 2 and 3, you have two groups attached to carbon-carbon double bond. In this case, you have two hydrogen attached and you have only one group attached to it. So I'm going to leave the explanation, or I have to tell you which one is more stable at this point, and then you will face this again when you were talking about like Markov and anti-Markov addition also. But just know that if the carbon-carbon double bond is attached to more R groups, more groups around carbon-carbon double bond, is going to be more stable. But at this point, if we just compare the intermediates, the intermediate that is coming from secondary allelic is going to be more stable than primary allelic. So we get two products also. Regardless, if we have racemic mixture, or we have like a or not, if this carbon is asymmetrical or symmetrical, we get mixture of two products because we have allelic alkyl halide. So allelic alkyl halide is going to give you two products if it goes through Sn1 reaction. So if you have Sn1 reaction, you get two resonances for intermediate, and as a result, two products, because each intermediate can go through resonance. Sn1 and Sn2. The Sn2 comparing so far, for Sn2 is one-step mechanism. Sn1 is a stepwise mechanism with formation of carbon as intermediate. The rate of the general rate equation or rate law for Sn2 reaction is a bimolecular. That means concentration of the alkyl halide, concentration of nucleophile, both of them are involved in the rate determining step. For Sn1 is unimolecular rate determining step, and we had the formula already. So rate equals K concentration of Rx only. For Sn2, rate equals K concentration of Rx times concentration of nucleophile. For Sn2, there is no formation of carbocation, and there is no rearrangement of the carbocation. But for Sn1, we have rearrangement of carbocation. There is a chance for rearrangement of carbocation. And I will give you example of what's going to happen for the rearrangement of carbocation. For Sn1 product, in terms of the stereochemistry, you have the retained and inverted configuration. For Sn2, is only inverted. So it's like an Umbra effect or Walden inversion that is going to change the configuration from reactant to product. That's for Sn2 mechanism. The reactivity order for Sn2, methyl and primary are the best. For Sn1, methyl and primary are the worst type of alkyl halide. Tertiary is the best one. For Sn2, tertiary is not good at all, and often it doesn't happen. It doesn't go through the Sn2. If you have a tertiary alkyl halide, it doesn't go through Sn2. If you have a methyl alkyl halide, it never goes through Sn1. Is it this slide? Yes, okay. Okay. In Sn1 mechanism for this reaction, for Sn1 mechanism, what's going to happen first? What's going to happen first? You tell me, what's going to happen first for Sn1 mechanism? Very good. So if we have the H2O reacting with this compound, first the alkyl halide would change to carbocation. Would change to carbocation. And you would expect this product to form. But often that's not going to happen. What's going to happen is you will get OH here and cis. So this is what you expected so far. You say the leaving group leaves, nucleophile comes in, and then it comes as H2O, you remove the H plus, and then you end up the net result of OH and the carbon that it was carrying halide. Now it carries the OH. But how do you explain this product? If you say you get this product instead of that expected product, this product is our unexpected, but it's going to be the major product. What makes the product to be, this is called rearranged product. Okay, this is the rearranged or the product as a result of rearrangement. So if we take one step back and I remove the OH at this point, this is going to be plus charge, right? if we don't have the OH. If you don't have this OH, we're going to have a plus charge here. This is a secondary carbocation. This one is a tertiary carbocation. So our secondary carbocation has inverted to, or being rearranged to, tertiary carbocation. So instead of you drawing like the normal arrow, you would say like this, has been rearranged. So a rearranged carbocation or rearranged intermediate. What is the benefit? The benefit that is going your carbocation, because you're looking for a stable carbocation, your carbocation is going from secondary to tertiary carbocation, so it's more stable. And that is expected to happen because you already have carbocation, and when you have carbocation, there's a possibility for it to change to tertiary, is going to change to tertiary. But how did the plus charge move to the next carbon? The plus charge is going to shift to the adjacent carbon, or it could shift to adjacent carbon if there is a benefit. That means if you have primary going to tertiary, it will happen. If you have secondary to tertiary, it can happen. The plus charge will shift to the next carbon. What are the conditions? The condition for that is the adjacent carbon must have either a hydrogen or it must have like a methyl group. But if it does have hydrogen, hydrogen is going to be better option to switch between the two carbons. So basically it's a shift. And the shift is called hydride shift. Hydride shift. What is the difference between a hydride and a hydrogen? H is a hydrogen, H plus is a hydrogen ion, H minus is hydride. So when you say hydride shift, that means a hydrogen with pair of electron moves to the carbon that is positively charged. The plus charge moves to that, replaces that hydride from the adjacent carbon. Is that clear? Because it's important for you to know under what condition shift can take place and what should be the benefit. The benefit is that it's going from a secondary carbocation to tertiary carbocation. The condition that you must have a hydride attached to that carbon, that plus charge is going to be replaced or is going to be shifting. So if H moves with the pair of electron or replaces the plus charge, this is called hydride shift. We could also have a methyl shift. Which one is easier, hydride shift or methyl shift? Hydride shift is much easier because you're dealing with a smaller group being moved from one carbon to another carbon. If you have to move like a 50-pound weight, it's going to be much easier for you than moving like 150 pounds. If you have another weight that is like 150, 50 is much easier than the 150. So it's the same idea here. Hydride shift is much easier than methyl shift. So in this case, you have a choice of a hydrogen and you have a choice of a methyl group. Which one is definitely? It would be the hydrogen shifting to the other carbon, and it's called the hydride shift. It's called rearrange. So the rearrangement is a possibility. So when it says here carbocation rearrangement, that's what actually means. If you have allelic, you will get rearrangement. If you have benefit of going from secondary to tertiary or primary to tertiary, you will have carbocation rearrangement. And the carbocation rearrangement, it comes from hydride shift or methyl shift. When would reaction go through Sn1, and under what condition it will go through Sn2? If you have a methyl or primary, you would get Sn2 only. If you have aryl halide or vinylic halide, these are not good. That's different from allelic. So that means you have a CC double bond and the halide is attached to this double bond. You cannot have a plus charge on this carbon. This carbon cannot carry a plus charge. Look at this carbon. It's a plus charge on the carbon double bond. Not stable, not good. Why is not stable? Because I use this example as saying, like, let's say you have lots of money in the bank, but you sleep hungry because you cannot use that money. It's not pleasant, is it? So if you have a lot of money and you cannot use it, you're not allowed to touch it, it's not going to make you very comfortable. And you can't sleep hungry with lots of money in the bank. So plus charge on carbon-carbon double bond is not stable. Same thing with this aryl halide. That means you have halide attached to carbon-carbon double bond in a benzene ring. A lot of electrons here, and then the plus charge on this carbon is going to be, again, a disaster. Just like a plus charge on oxygen is not good. So we have if we have alkyl, is going to be Sn2 only. If we have tertiary halide, it would be Sn1 only. Benzylic and allelic going to be Sn1 only, because benzylic and allelic carbocations are very stable. So if you have allelic carbocation, this carbocation is allelic and is very stable. Why is very stable? Because it can form resonance. Because it can form resonance makes it more stable. Remember, more number of resonances, more stable, intermediate, and that happened with the acid also, definition for acid or conjugate base. So if you have allelic or benzylic, Sn1 only. If you have tertiary, it would be Sn1 only. If you have methyl or primary, is going to be Sn2 only. Now, the gray area here, the gray, so the tertiary benzylic and allelic, definitely Sn1. For the gray area is when you have if you have secondary. What's going to happen when you have secondary? Because there is no specific direction for secondary. For secondary, would it go to Sn1 or would it go to Sn2? Then you have to change the condition of the reaction. So if it's not definite by the table that is going to be Sn1 only or Sn2 only, then it's going to be depending on condition of the reaction. Now it depends on your solvent and it depends on your nucleophile. So it depends on the concentration of the nucleophile. You increase the concentration of the nucleophile, it can go to Sn2. If you reactivity of the nucleophile, a stronger nucleophile is going to promote Sn2, and the effect of the solvent also, the solvent can affect also Sn1 or Sn2. So when there is a competition between the Sn1 and Sn2 for secondary alkyl halide, it depends on the solvent also. So if it depends on nucleophile. If you have weak nucleophile, it will go to Sn1. If you have a strong nucleophile and you have high concentration of nucleophile, it will go to Sn2. Something is happening here. I don't know. It has to do with the weak connections. I hope I don't lose you guys. So good nucleophile Sn2, weak nucleophile Sn1. Examples of weak nucleophile. You have to memorize these. H2O and CH3OH. These are very stable. They are compound on their own. They can act as a nucleophile because pair of unshared electrons, but these are not a strong nucleophile because they are stable on their own. A strong nucleophile is something that is not stable on its own, and if it attaches to positively charged center, is going to become more stable. Like hydroxide is a strong nucleophile because it's not stable on its own. Alkoxide. What is alkoxide? Alkoxide means you have alcohol, but you remove the hydrogen, and that makes it alkoxide. Okay. Which one would be better for the Sn1 and Sn2? If you have polar solvent is good for Sn1. Non-polar solvent, they are good for Sn2. So another classification, like what is the protic solvent? These are examples of the protic solvent. So when we talk protic solvent, at least you know what we're talking about. These are the aprotic solvent. Protic solvent, they have a OH or oxygen, hydrogen attached to the oxygen. But when you have aprotic, that means there is no hydrogen attached to nitrogen directly or oxygen directly. So we have protic solvent and we have aprotic solvent. The more polar the solvent is, better for Sn1. You have access to all of these PowerPoints, right? Should have access to the PowerPoints, but here's the picture. You have non-polar. These are non-polar. These are polar solvents. Okay? Polar aprotic, and then you have polar protic. Polar protic is good for Sn1. And why polar is good for Sn1? Because for Sn1 you get carbocation, and if you have a polar solvent or protic solvent, it can stabilize the plus charge. So if you have polar solvent, your solvent is going to have a plus and minus. So if you have a plus and minus, then the minus side of the solvent, it can help to stabilize the carbocation. That's why polar protic, especially solvents, they are good for Sn1. If you have non-polar, if it's a non-polar solvent, you're not going to get. So solvent for Sn1, it must be polar. For Sn2, a solvent should be aprotic solvent. And the polarity, the more polar the solvent is, Sn2 would be less likely, Sn1 would be more likely. Because you don't have positively charged intermediate. So for Sn1, you increase the polarity, the faster the reaction. We have a table that you can look at it also. So for Sn1 reaction, look at the effect of the solvent. You increase the solvent, the polarity of the solvent, you get faster reaction. This is for Sn1. The more polar the solvent is, the faster the reaction is. So if you increase the percentage of ethanol. Basically, ethanol is less polar than water. If it's water, you get 1200, and then it decreases as you increase the concentration of ethanol. So polar aprotic solvents, they are good for, if it's aprotic, it's good for Sn2. But polar protic is going to be good for Sn1. Rearrangement, we talked about rearrangement. This is another example of the rearrangement. When the bromine leaves here, you get a plus charge, and that plus charge is going to be secondary carbocation. If there is a shift here, a hydride shift, that means the hydride would move to this carbon, plus charge would move to adjacent carbon. You go from secondary to a tertiary carbocation. So there is a benefit, and you are going to have a shift of the hydrogen. Hydrogen with the pair of electron, that means hydrogen. The other choice for the shift is the methyl shift. If this carbon has no hydrogen attached, but if you have a methyl group attached, then it can shift. The plus charge can go to carbon that is more substituted, that means attached to more number of alkyl group, and methyl can shift, replace the plus charge. So when the bromine leaves here, you have a plus charge that is primary. It can shift with the methyl to go from primary to a tertiary, and it's going to be a lot more stable. What about if you had no methyl and no hydride? No methyl and no hydride is like you're at the gym and there is only one weight there that is like 300 pounds or 500 pounds, and you cannot lift it. You just don't lift it, right? But if it's like a 10 pound, that's like a hydrogen or hydride shift. If it's like a 30 pound, that's like a methyl shift. And then you have something that is much heavier than what you have practiced before. You're not going to lift it. It's not going to happen. It takes so much energy and the chance for injury. In this case, for reaction, there is really no injury, but it takes a lot of energy to move ethyl group, propyl group, to remove the plus sign or to shift the plus sign. So it's not going to happen. So it just says it doesn't happen. No shift. So the shift only happens when you have chance for moving or replacing with the hydrogen. Or another summary of what we have talked so far. For Sn2, methyl and primary is good. For tertiary, secondary, and tertiary only, the methyl and primary is not possible. Strong nucleophile for Sn2, weak nucleophile promotes the Sn1. Sometimes the solvent can be used. Polar aprotic solvent is good for, remember, aprotic, okay, for Sn2, and then protic for Sn1. Rate of the reaction is bimolecular. Rate for reaction for Sn1 is unimolecular. For Sn2, we have inversion of the chiral carbon, changes to R, R changes to S. But for this one, if you start with R, you end up with mixture of R plus S. No rearrangement for Sn2, but you have rearrangement for Sn1. When does if you have a hydride shift or chance for methyl shift. So, two mechanisms already. This chapter is known as a 4-mechanism chapter. That's the Sn1, Sn2, E1, E2. So we looked at Sn1 and Sn2 already. What is E1 stands for, or E2 stands for? E stands for elimination type reaction. That's another reaction of the alkyl halides. And the 1 or 2, you already know from 1 and 2 from Sn1, Sn2. The 1 means unimolecular and 2 means bimolecular. For elimination reaction, we are not dealing with the strength of the nucleophile, we are dealing with the strength of the base. We need a strong base to remove hydrogen. Okay? We need a strong base to remove hydrogen. Where are we removing hydrogen? After the carbocation forms, we need to remove hydrogen from adjacent carbon. So when this halide leaves, you end up with carbocation here. You have two choices: either replace it with that nucleophile, you replace the leaving group with the nucleophile. The second choice is to remove a hydrogen, and when you remove a hydrogen from adjacent carbon, you are going to get, you are removing hydrogen, not hydride, you are removing H+. So the electrons from that hydrogen, it can drop in and form a pi bond. So you remove only the hydrogen from here. This pair of electrons that it used to form bond with the hydrogen is going to drop in, have a plus charge, and then you have a negative charge here. Plus and negative, the pair of electrons is going to be shared and the charge is going to be cancelled. As a result, you get alkene. So the product of E2 or E1 reaction is formation of alkene. If it's a single step reaction, that means the leaving group is leaving at the same time this proton is being abstracted. This reaction is called E2 mechanism. For E1 mechanism, carbocation forms first, and then you get you remove the hydrogen. And when you remove the hydrogen, then double bond is going to form. What makes the E2 mechanism versus E1 preferred is the strength of the base. You must have good leaving group. Good leaving group is going to help for both of them, but the better the leaving group, the faster the reaction is going to be for E1 and for E2. So the hydrogen from adjacent is going to be removed. Just keep that in mind. And the new carbon-carbon double bond is going to form. The better the leaving group, the faster the reaction. If the halide leaves first, then you end up with carbocation, and then you have two-step reaction. In two-step reaction, you have multi-step or a stepwise reaction. You again have a slow step and fast step. The fast step has lower activation energy, a slow step has greater activation energy. Basically, formation of carbocation in this case is going to be the rate determining step. Which one would go through one mechanism faster, tertiary or secondary? Which one would go through E1 mechanism faster, a tertiary or secondary? Do we have an intermediate for E1 mechanism? Yes or no? For E1 mechanism. For E1 mechanism, we have intermediate. And if we do intermediate, what type of intermediate you have there is a carbocation, right? It's a carbocation intermediate. So which one would form more stable intermediate, a secondary or tertiary? A tertiary would form more stable intermediate. As a result, tertiary is going to be faster. It would go through the E1 mechanism faster because you have more stable intermediate. So tertiary would go faster because of the stability of intermediate. So you have two-step reaction: formation of carbocation And then it's going to be removing of hydrogen from adjacent carbon. Regio selective. What does it mean? We just said adjacent carbon is going to lose hydrogen, but which adjacent carbon? The one on the right side. For 3 carbon is not going to make a difference. You have only one product, propene. It doesn't matter carbon-carbon double bond forms between on the right side or on the left side. So tertiary better than secondary, better than primary. For E1 mechanism, definitely yes. For the E2 mechanisms, now the Regio Specific or selective hydrogen would be removed easier. To remove the hydrogen, which one is going to be removed easier? If you look at this percentage of the product, percent composition of the product, because for 2-bromo butane, you actually, when you get the plus charge here, you have 2 choices: to remove the hydrogen from the left side or to remove the hydrogen from the right side. If you remove from the right side of the carbocation, you end up with this product. You have carbon-carbon double bond with 2 alkyl group attached to it. If you remove the hydrogen from the left side, you end up with carbon-carbon double bond with 1 alkyl group attached. Which one is more preferred? Carbon-carbon double bond, which one is more stable? Carbon-carbon double bond with 2 alkyl groups or with 1 alkyl group only? Based on the energy diagram, when you have, or based on internal energy, if you compare the energy of this molecule with this molecule, experimentally it's found that molecules or alkenes or carbon-carbon double bonds with more alkyl group attached to it is going to be more stable. So more stable product, that's benefit, right? The more stable the product is, more energy is going to be released, is going to be more exothermic because it's going to go lower energy on the product side. Less stable product is going to be minor. So now we have with 2 factors. One is stability of intermediate. Second is stability of product. So both of them is going to determine which one is major product. More stable intermediate would yield major product. More stable product is going to yield major product also. Depends on what situation we are dealing with. For E1, we get carbocation, so we have intermediate. The product that is coming from tertiary is going to be faster. When we come to E2 mechanism, we don't have carbocation intermediate, but we have to look at the stability of the product. Which hydrogen should be removed in order to get more stable product? So the answer is remove the hydrogen from adjacent carbon. So which adjacent carbon? Remove the hydrogen from adjacent carbon, that when you know a carbon-carbon double bond is going to form, you get more number of alkyl groups attached to the carbon-carbon double bond. %, versus 30%. You have 1, 2 group attached, and you have 2 group attached. In this case, you have carbon-carbon double bond, basically. Both of them are on the same carbon, and then this is the this carbon, the one of the carbon from the double bond has no alkyl group, so you have that CH2. So if you have 2 alkyl groups, choice of this one is 3 alkyl groups, so you get 2 alkyl groups here and 2 alkyl groups on that side. So it's going to make this one more stable. More number of alkyl groups around carbon-carbon double bond, more stable the product. So the major product of E2 reaction is the most stable alkene. What makes the alkene more stable? The greater number of alkyl group attached to carbon-carbon double bond. So you have one alkyl group here, and here you have two alkyl groups. Again, major product. More stable is the alkene or carbon-carbon double bond attached to greater number of R groups. Okay, which one is more stable? This is one alkyl substitution, two alkyl substitution, and you have three alkyl substitution. So this is going to be more stable. So three alkyl is going to be more stable than alkyl group, more stable than one alkyl. If I say R here versus hydrogen, R means alkyl group. So when you have four R groups, it's going to be the most stable. Okay. So just know this trend here. 4R is going to be most stable, then 3R, then 2R, then 1R, and then this is a no R, non-substitute. It's not substitute at all. Now, what about when you have two R groups? When you have two R groups, you have two conditions, and that could be two R groups on opposite side or two R groups in the same site. Basically, you have a cis and trans. Which one is more stable? Trans is going to be more stable than cis. If the base that you are using is bulky, then a bulky base is not going to be able to take away the more substituted hydrogen. As a result, then you end up with a group that is less substituted, but you don't have a choice, and that would be the major. So exception. So if you use a bulky base, when you bring a bulky base is going to remove the hydrogen that is more accessible, the hydrogen that is easier to be removed by a bulky base. This type of product is known as the if you end up with the most stable as the most substituted, it's called a Sn product, rule or Sn product. If you bring a bulky base to remove least hindered hydrogen, that is going to be like anti-Sn product, or is going to be, it's called Hoffman product. Use of bulky base on less hindered alkyl halide. So if you want to use a bulky base, it's going to remove the hydrogen from easier side. So this is the secondary, this is the primary. The primary is going to be removed by bulky base. E2 reactions, you will get more substituted R group of the alkene as a product. So depends on the nature of the base. If you use a like very bulky base, then you have to go with the less substituted. So the more bulky the base is, the product is going to be less substituted. So when you have two choice, it depends on the base you are using. But if you use bulky base, like extremely bulky base, that's the only purpose that you are using bulky base, if you want to make sure that the product is unsubstituted or less substituted product. So what makes this product to be a minor product? When you have an E1, that is going from formation of carbocation and stability of the carbocation. Then you have minor product, major product. For E1, CH2 on the end rather than a CH3. So that means Hoffman product, right? That would be for when you are with the bulky base. So if you get a CH2 at the end, that is less substituted, and that would be your minor product. Your major product is when you have CH3 at the end. So that means that the CC double bond is not at the end of the carbon chain, is in the middle. The more substituted alkene, when you remove the proton from a carbon, is going to form faster. It was so hot here today that I keep sweating. But so for E1, tertiary is going to be, this one is a better or more comprehensive. Okay. So tertiary benzylic, definitely E1. Tertiary allelic, definitely E1. You have a secondary benzylic and secondary allelic, which is, in terms of the stability, they are very similar to tertiary regular. So this is going to be Sn1. And then benzylic and allelic, the similarity or stability of benzylic, if it's primary benzylic or primary allelic, is as stable as a secondary carbocation. And then you have the primary, and then vinyl is the least stable. Vinylic, again, least stable. So leaving group is going to help both E1 and E2. Primary alkyl halide, secondary and tertiary, it could be either one of them. Okay. So for primary alkyl halide, E1 is not possibility. E2, it's possible, but it doesn't give the most stable product. A strong base is going to help elimination, and a protic solvent is going to help the E2 mechanism. Protic solvent for E1. So E1, Sn1, E2, Sn2, in terms of the solvent, they are very similar. So the solvent effect for E1 is same as Sn1. Solvent effect for E2 is same as Sn2. So if you know the factors for Sn2 and Sn1, they are very similar to the E1 and E2. Okay, let's look at the composition for reaction that is going to help us which hydrogen would be removed. The abstraction or elimination is anti-coplanar. So if you have the hydrogen and halide on the same site, is not going to happen if it's like you have them on opposite sides. So that's basically for the E2. It's easier to remove the hydrogen from the opposite side. So that's you're going to get the anti-coplanar abstraction. So hydrogen from the opposite end is going to be easier. Which one is going to happen, substitution or elimination? So you have, is this like a study of the 4 mechanisms versus Sn1 versus Sn2, E1 versus E2, what are the factors that is going to make one more significant? And then lastly, do they take substitution or elimination? Because we said the solvent condition for E1 and Sn1 is the same, and for Sn2 and E2 is the same. Now, if you want to make it substitution, what's going to happen? How can you change the condition of the reaction? If you want to make it elimination, how could you change it? High temperature favors elimination over substitution. That's like one of the major differences. So high temperature always elimination. If it's a primary alkyl halide, it's going to go Sn2 versus E2. Primary cannot go through the E1 or Sn1 because it doesn't form carbocation. If you have primary alkyl halide, Sn2 is actually would be better than the E2 because of the CHM of product, because then you have less substituted product. Aprotic polar solvent is good for both of them, and for Sn2 and Sn1, protic solvent is going to be good for E1 and Sn1. Now, it depends if you are aqueous or if you have alcohol. So we have to have a point of difference. So high temperature is good for elimination, and then your solvent, is it aqueous solvent or is it alcohol solvent? Which one is better for elimination? Which one is better for the substitution? When it comes to the elimination, protic solvents are good for. Protic solvent is going to be good for the or strong base is going to, a strong nucleophile is going to go with the strong nucleophile. It will go for substitution. A strong base will go to elimination. So those are 2 factors so far: elimination versus the substitution. High temperature elimination, a strength of the base versus a strength of the nucleophile. So if you have a strong base, it goes elimination better than substitution. A strong nucleophile, it goes for substitution. For both E1 and E2, you realize that tertiary is better. For E1, because it gives you better carbocation, more stable carbocation. For E2, it gives you safe product. So if it's tertiary, the chance for tertiary to have a more stable product is higher. So for both E1 and E2, tertiary is better than secondary, better than primary. Sn1 tertiary, and then for Sn2 is primary. So if you have a primary alkyl halide, then it's going to be, you see, I think I have a table here. So effect of the temperature, and then a tertiary for elimination, higher temperature for elimination, strength of the base. So the stronger the base is going to be elimination. A strong nucleophile would go to substitution. I have a table. If you have weak nucleophile, it's going to be either Sn1 or Sn2. Aqueous is going to be better for substitution, and alcohol is going to be better for elimination. Yes. These tables are going to help you, like, to find that it's going to be, like, if you have a primary, it's going to help you to answer multiple choice questions basically faster if you kind of memorize these, and these are kind of tricks. So if you have a primary, alkyl halide is not going to go through Sn1 or E1. If you have tertiary, it's not going to go through Sn2. The steric hindrance means that you have too many groups attached to your carbon carrying the halide. So if you have 1, 2, 3, R group is sterically hindered, but if you have hydrogen, it's not hindered. So if you have the halide here and 3 hydrogen, this is not hindered. The smaller the size of the group attached to carbon carrying the functional group, the smaller the size of this group, it means less hindered. Now, if you have a methyl group versus ethyl group or propyl group is going to make it more hindered than the ethyl group, than the methyl group. So the bulkier the group attached to the carbon is going to make it more hindered. So steric hindrance is not good for Sn2 type reaction, is not good for E2 either. Okay, steric hindrance. Okay. Questions? No questions? It's a lot of information, and this is, again, as I said, it's a very important chapter because it helps you to understand the mechanism of reaction. What you want to know by heart is that the more stable intermediate, first of all, you need to know what is intermediate. What is intermediate is a species that it forms in the reaction process and is consumed right away. You cannot isolate it. Talked about the intermediates in chapter 2. Those are carbocation, carboanion, free radical, and chapter 4. Free radical is intermediate, carbocation is intermediate, carbanion is intermediate. You need to know the trend and stability. Which intermediate is more stable? If it's carbocation, tertiary would be more stable. If it's carbanion, primary is going to be more stable. So when you say Sn1 reaction, that means multi-step or stepwise reaction. You get intermediate, and the intermediate that is forming is carbocation. So a tertiary is going to form faster. A more stable product is going to be major product. That's like for E2 mechanisms. When you get alkene as a product, alkene that more substituted is going to be faster, is going to form faster. For Sn2 type reaction, because there is no intermediate, is a transition state. During the transition state, nucleophile is coming in, leaving group is leaving, because your carbon is going to form 5 bonds temporarily. So it's going to be engaged with 5 groups. The less hindered that carbon is, the better off it's going to be in terms of the energy. It's going to be more stable if it's less hindered. So that's why methyl and primary it's going to be the best for Sn2 type reaction. Sn1 is not going to happen for methyl and primary. If you understand the mechanisms, then you can answer the questions based on the concept. But if you don't understand the mechanism, then you cannot answer. You will be, especially the questions are going to be different from one student to another student. So as a result, you're not going to be able to get the answer correctly. It's going to be not tricky questions, but since they are changing, just one thing change, one condition changes, then you won't be able to answer the question unless you understand the mechanism. So if you know for E1 and Sn1, the mechanism is formation of carbocation, then you could say polar protic solvent is going to stabilize intermediate, because you have a plus charge for your intermediate, and if you have negative charge around it, it's going to stabilize it more. But if you don't have intermediate, then you don't need the polar protic solvent. You don't need the negative charge coming from your solvent to stabilize it. So if you understand the mechanism, it's going to help you for concept, if it makes sense. So there are 4 mechanisms: E1, E2, Sn1, Sn2. If you know about Sn1, Sn2, so study like much harder for Sn1, Sn2, and then you expand your knowledge. So if you already know Sn2, means that nucleophile comes in at the same time leaving group is leaving. For E2, the only thing changes, base is attacking at the same time leaving group is leaving. So it's very similar. And then for E1, if you know for Sn1, carbocation forms first and then the nucleophile comes in, for E1, carbocation forms first and then hydrogen is abstracted from adjacent carbon. Possibility of rearrangement: anytime you have carbocation as intermediate, there is a chance for rearrangement. Okay. Any other questions? You're welcome. Okay, I'm going to stop the recording. I just need to, I also, they showed me how to record the attendance